if screen sharing works. So this is the recent photo taken at some group gathering in China. So in 5 years, we built an international center for polaritonics, world first. And in this center, we study liquid light. And so today I will tell you what liquid light is and how it can be used to make a quantum computer. This is an outline of my talk. I will introduce the main character of this story, exciton-polariton, that is a quasi-particle that can be called a quantum of liquid light. And then I will present the concept of qubits based on exciton-polaritons, on liquid light. And I will tell you how these qubits are now being experimentally studied, realized, and put together to make quantum networks and quantum simulators. So this is a work in progress. There is no yet ready quantum computer, but you will see that the progress is quite fast, actually. So to start with, what is an exciton-polariton? First of all, what is an exciton? An exciton is very similar to a hydrogen atom, but if a hydrogen atom is formed by a proton and an electron, an exciton in a semiconductor is formed by also a positively charged quasi-particle called hole and an electron, that is the electron in the conduction band of the semiconductor. They are bound together by Coulomb attraction, exactly as proton and electron in the hydrogen atom, and they form this hydrogen-like particle that is much larger in size than a hydrogen atom. The typical size of an exciton is 100 angstrom. And also the binding is much smaller. So the Rydberg constant for an exciton is maybe 100 times or 1,000 times smaller than for the hydrogen atom. But also the main difference is that these excitons, they do not live forever, because an electron and the hole can disappear. They recombine, and the energy of exciton is released, and it can be released in the form of a photon. So if the exciton recombines, a photon is emitted. But if we are still in the semiconductor or in a semiconductor structure, this emitted photon can be reabsorbed and it can create the exciton again. And then this exciton can again emit a photon, and the photon can be again reabsorbed, and so on and so on. So from the point of view of quantum mechanics, you can never tell before you do the measurement. You can never know where and when you have an exciton and where and when you have a photon. Only when you do the measurement, you find this entity in a state of exciton or in a state of photon. Before that, it exists in a quantum superposition of a matter quasi-particle, that is exciton, and a quantum of light, that is photon. And that is why the properties of these exciton-polaritons, they are inherited both from light and from matter. They combine properties of light and matter. So as matter particles, they can interact with each other, but as light, they can propagate with a high speed. They can have polarization, phase. They can be described by wave equations, basically, like any light. So at the end of the last century, it was proposed that exciton-polaritons, being bosons, bosonic quasi-particles, they can form bosonic condensates. And Bose-Einstein condensates are such states that that are composed by many particles, but all these particles are in the same quantum state. So they have the same energy, the same wavelength. And it was first theoretically proposed, and then it was realized in a variety of structures. And interestingly, it was also realized at room temperature. I underline that before that, in 20th century, the phenomenon of Bose-Einstein condensation was only observed in atomic gases at ultra-low temperatures of the order of nanokelvin. But here in semiconductor structures, we can have a Bose-Einstein condensation at room temperature. And this is very interesting because this coherent many-body effect, it can be brought to the everyday life. It is no more exotic. It is no more a matter of just research in laboratories, but it can be used potentially. So how can it be used? The first idea was to make low-threshold lasers, and indeed lasers were done, but the niche for applications is not so large of polariton lasers. However, when working on lasers, we discovered that actually this is a fantastic system to play with wave functions. Because polariton condensates, they can be characterized by many body wave functions, and these wave functions can be observed in optical experiments. As it is shown on this slide, this is an experimental work where in a trap, in a parabolic trap, you see more than 10 quantum confined energy levels. All of them are occupied by the condensate of exciton-polaritons. And by doing so-called tomography, spectral tomography measurement, you can visualize a wave function of the condensate at every level, every energy level, from the first to the seventh, as you see here, and even higher. So you can see it and you can engineer it. You can change the shape of a trap, and then your wave function would change. So you can put it in a shape that you need. And this, the coherence of this state, it is preserved over macroscopic time. Even if each individual exciton-polariton, it lives not so long time, maybe a few tenths of picoseconds, and then it disappears by going away from the structure, tunneling through the mirrors. The whole condensate, it can live forever. Some particles go away, but some particles come in if you have pumping, and the condensate persists, and it keeps coherent over all time of its life, and it can live potentially infinitely, provided that it is constantly pumped. So this offers a tremendous opportunity to use these very stable, coherent states for quantum information processing. And first works, well, during the last decade, were devoted to the creation of arrays of polariton condensates. They were realized by etching of semiconductor structures or by localization of polariton condensates in optical traps. There are different methods, and actually they were very successful. So here on this slide, you see an array of 1024 condensates, polariton condensates, and they are created by optical pumping, but non-resonant. So the optical pumping just creates electron-hole pairs, which are not excitons and not coherent. And then themselves, they self-organize, they form excitons. Excitons start emit light, and light is being reabsorbed. So you have these polaritons. And in each point, each bright point of this picture, you have maybe 20,000, 30,000 exciton-polaritons sitting in the same quantum state, sharing the same quantum state. And what is even more interesting, this array of condensates can be fully phase-locked on a time scale of 100 picoseconds, so 10 to minus 10 seconds. These self-organized states, they find some arrangement so that the phase relations between every two condensates is fixed, and it does not change with time. So it can be experimentally measured, and you have plenty of time to measure it because it exists forever. Until you keep pumping the system, it doesn't change. So it was realized that the specific phase configuration that is chosen by the system minimizes the so-called XY Hamiltonian, which is interaction Hamiltonian of two-dimensional spins. And this theta is an angle between spin number I and spin number I plus 1. So two vectors, there is an angle theta between them, and the Hamiltonian it contains cosine of this angle. So it is a very complex Hamiltonian if you have 1,000 terms in it, 1,000 condensates. But actually more than 1,000 terms, of course, because you have 1,000 condensates, but each of them can interact with many others. But still, the system finds the ground state of this Hamiltonian on a time scale of 10 to minus 10 seconds. And this is a tremendous opportunity for the realization of a simulator. So a device that solves one specific problem, but solves it much faster than any classical computer or supercomputer. So that was a proposal of 2017. And I should emphasize that while it is very interesting, it is not yet a quantum computer, and it is not yet anything quantum because there is no qubits here. A condensate is not a qubit, but a qubit can be prepared from the condensate. And for this, we need to exploit the superfluidity of polariton condensates, superfluidity of liquid light. This effect, very similar to the superfluidity of liquid helium, it was experimentally observed back in 2008-2009, initially at low temperatures, but now it is also observed in perovskite, for example, microcavities at room temperature. And the effect of superfluidity is basically the coherent effect. This superfluid liquid does not see obstacles. It moves without friction, without viscosity, and it can form, for example, vortices that exist forever, circular currents that exist forever, because liquid moves without any resistance, without any friction. And this is what can be used in qubits. The idea is very similar to what is realized already with superconductors. Also in the superconductors, you can have a current that propagates forever without any friction, without any resistivity. And the same with the superfluid. The only difference is that a superfluid current, it does not carry electric charge. Our exciton-polaritons are electrically neutral. But if you put them on a ring, they can be characterized by a phase. And the phase, this macroscopic phase of the whole ensemble of tens of thousands of particles, it must be a continuous function of the coordinate. So if you go around the circle, it must change by an integer number of 2 pi. And this is very similar to what happens in a superconductor. So in a superconductor, they pass a magnetic flux, and if this flux is equal to half quantum, then realization of clockwise and anti-clockwise currents that enhance the magnetic flux to the full quantum or suppress it to zero. So the realization of these two currents has equal probabilities. And the system, if there is some Josephson junction that mixes currents, it has two new eigenstates, which are superpositions of clockwise and anti-clockwise currents. So on these superpositions, they build superconducting qubits, which are very, very popular now and used in Google quantum computer, in IBM quantum computer, in Chinese quantum computers. And the same can be done, conceptually the same with the superfluid qubits. Just instead of magnetic field, we use so-called weak link that pins a dark soliton. And a dark soliton is characterized by a phase jump by pi over 2. So the phase on the circuit would change by pi here in the point of defect, and then it should change by either pi or minus pi when you go around the circuit. And these two solutions are degenerate, but this degeneracy can be lifted because of this weak link. And again, you have two states which are superposition states of two superfluid currents, clockwise and anti-clockwise, and you can make a qubit. So to make the long story short, one can say that in a superconducting qubit, in every qubit, something must be quantized. Yes, this is a quantum object, so something must be quantized. But in a superconducting qubit, it is the magnetic flux that is quantized. But in a superfluid qubit, it is a topological charge. Topological charge tells you how many times the phase changes by 2 pi when you go around the circuit. So quantization of topologic charge is at the heart of these polarity qubits, which have been proposed by our group in China in 2021. Then the realization came very soon because ring condensates, ring polariton condensates have been already studied by then. They realized in micropillars and they demonstrate persistent superfluid currents with different topological charges. Here you see the currents with charges +1 and -1 that manifest themselves in interferometry spectra of this condensate. So the phase, how it changes as a function of coordinate, it can be deduced from interferometry measurements. And this technique is well established. Now, when it came to realization of qubits, of course, a lot of work had to be done to optimize the trap where this condensate would be formed. And the most flexible are optical traps. So here we have studied elliptical traps that are optically induced. And the energy spectrum of the condensate in this elliptical trap, it consists of many discrete energy levels, but we choose two of them that lie closely. And on these two states, we realize the qubit. How to control it? The idea came from the group of Pavlos Lagoudakis in Skoltech. They control the state of a qubit by rotating the trap. If you have an elliptical trap and you manage to rotate it, then you make realization of a current propagating in the same direction as the direction of rotation preferential. So how to rotate it? By optical methods. You create a trap by a superposition of two excitation beams, and both of them are Laguerre-Gaussian beams that carry orbital momentum, +1 and -1, and they are slightly detuned in energy. Due to this detuning in frequency, in energy, the trap, the potential, the combined potential that is created by these two laser beams, it rotates. And you can control the speed of this rotation by controlling the detuning between these two laser beams. So you can rotate it clockwise, you can rotate it anti-clockwise. And this group, they observed that the probability of generation of clockwise and anti-clockwise superfluid currents is exactly the same if the trap does not rotate, so 50-50. But if it rotates, so preferentially you start generating the currents that propagate in the direction of rotation. And then really you can achieve 100% of, in 100% of cases, or almost 100% of cases, the superfluid current would go, for example, clockwise. But if you change the speed of rotation to the opposite, then you will have 100% of anti-clockwise current. So this is a switch. You can control the state of your qubit. Now, if you created it already, you initialize it. You can also swap the direction of rotation by sending a pi pulse of light. Pi means it is a half period of full oscillation between clockwise and anti-clockwise direction. So in this case, it is about 100 picosecond duration of a pulse. And Mark Assmann in Dortmund, he observed in this paper the switching between current of one direction to current of the other direction, passing by some so-called dipole states. And this basically, this is the logic gate. This is the logic gate, a single qubit logic gate that can be used in future polariton quantum computers. Now, to build a quantum computer, we need single qubit gates and double qubit gates. So the next step was to realize double qubit traps. So two elliptical traps together. And the energy spectrum of two elliptical traps together, it shows also many states, but we choose 4 that form this group that stay together. And on these 4, we build our 2 qubit gate. And the main problem here, how to read out the information of this qubit. So it is done optically. Light that comes out of this unknown state of every qubit, it passes through the phase mask. SLM, special light modulator, creates a phase mask that sets a basis in which you measure your state. Then, if the state of the condensate coincides with the state of the phase mask, then after the phase mask, you have a Gaussian beam that passes through the optical fiber, a single mode optical fiber. Then it comes to the photomultiplier, and you have some signal. You say 1, signal equal to 1. But if the state of the condensate does not coincide with the state of the phase mask, then you have not a Gaussian beam, but maybe Laguerre Gaussian, and it doesn't go through the single mode fiber, and you have a signal equal to 0 on the photomultiplier. And when you have 2 qubits, you do separately these measurements for the first one and second one, and you change the basis for them. So usually there are 2 bases chosen for one and 2 bases chosen for for the second one, and altogether this experimental setup allows you to feel a 4x4 matrix that is the measurement matrix of double qubit. So first experiments like this have been realized in Russian Quantum Center by Roman Cherbunin, and this work is now in progress also in China. So altogether, if it works, it would give us a polariton quantum computer. And how it operates is shown on this slide. There is a lot of text here. I'm not sure I have time to read all this, but basically the idea is that you have non-resonant optical pumping that just creates electron-hole pairs, and it creates also the network, the potential on a planar microcavity. So with light, you just draw the potential. And in this potential, your polariton condensates start forming. So initially, when the first exciton falls into the set of polariton modes, it does not go to one specific mode, because one specific mode would have some percentage of exciton and some percentage of light. Initially, you have no light, you just have an exciton. So it will be necessarily distributed as a superposition between many states. So then this superposition, it can die, the exciton can disappear, but it can also survive, and it can be amplified by new excitons, more excitons coming to the system. This is a stimulated scattering process that is responsible for creation of exciton-polariton condensates. So the condensate grows, and it is in a superposition of 2 or several states in a trap. And this is the initialization of our system, multi-qubit system, that is prepared in some specific quantum state that we need. So the condensates interact with each other, usually nearest neighbors. So far, we cannot couple next nearest neighbors, but we are working on that. And due to these interactions, already the system starts performing some calculation, but you can also control it by light pulses of chosen duration. And so you can switch quantum states of individual condensates, and you can affect also condensate interaction. And this is how you realize logic gates. The most challenging is, of course, 2-qubit logic gate like CNR or ISWAP. And this is so far the main goal of our experimental research, to realize this gate. Then at some stage, this system, it becomes classical. It is projected to the classical basis. For example, that the basis actually you can choose with also with special light modulator. You set the basis in which you detect the system, to which you project the system. So the system with quantum superposition, it is projected to the classical basis at the stage of readout. But what is very important is that after readout, the system survives. It just stays in that state, and it can stay forever until you switch off pumping. And this is very important because this is memory. So the polariton system is very powerful because it combines the possibility of doing quantum operations, quantum simulations, but also once it becomes projected to the classical basis, then you keep in memory this the result, the solution, and you can keep it for a long time, as much as you need. So that was, of course, the concept. The realization, it is now being done. So here are 4 coupled qubits already realized, and here are 22. So again, a tremendous breakthrough in the group of Pavlos Lagoudakis in Skoltech to appear in Nature Communications very soon. He managed to couple 22 polariton qubits on a hexagonal lattice. He, by single-shot interferometry measurements, he demonstrated stochastic behavior. So each time the measurement was projecting the system to some classical state that is shown by this red and blue arrows showing the direction of vortices or circular currents, clockwise or anti-clockwise. And each realization was different from the other. So clearly he had a superposition state initially, but when he was doing the measurement, each time it was projected to one of possible classical realizations. And then one can, of course, study statistics of this system and see what happens when you change initial conditions, etc. So this system is not a quantum computer. There is no logic gates here, but there are 22 coherently coupled qubits. So this is a simulator. This is a quantum simulator. And actually what it simulates an Ising Hamiltonian, because every vortex can be mapped to a spin that has 2 classical projections up or down that correspond to clockwise and anti-clockwise direction of current, of polariton current. And with this system, you can find a minimum of quantum Ising Hamiltonian. So for 22 coupled qubits, it is still within reach of classical supercomputers. The threshold is somewhere at the level of 25. And if we would go beyond 25, then this system would hopefully demonstrate a quantum advantage. So it would find the minimum of a Hamiltonian that is impossible in a reasonable time to solve with a classical supercomputer. So then we are looking further. We are looking for universal quantum computer and realization of simple algorithms. So the programmable quantum computer, and the simplest one is Deutsch algorithm that doesn't require many qubits, just a few. And our collaborators, they predicted the fidelity that is rather high of these measurements, but this is yet to be implemented experimentally. And well, other polariton quantum protocols, they're being studied theoretically. They're being modeled on classical computers, supercomputers, and they wait for the experimental realization. So this brings me to my conclusions. I wanted to convince you that liquid light is very, very promising for quantum information processing. And this is because actually the system is very flexible. First of all, these condensates and superfluids, you can realize them at room temperature in a variety of systems. So this is a great advantage with respect to superconducting qubits. Then you can control them fully optically. You can draw a network, set a network of coupled qubits optically. You do not need to make new and new structures, new and new processors for different networks. You just change a code of the special light modulator that creates this optical potential. And everything actually is done optically. Readout is optical. Switching gate operations are fully optical, which is convenient. And it ensures that everything is ultra fast and losses are small because light is very coherent compared to matter, to electronics. So this is a semiconductor-based technology. Semiconductor-based technologies are well developed. So this constitutes very significant advantages. But of course, this platform for quantum computation is in its infancy so far. We cannot yet compete with big platforms like superconducting qubits, just for the simple reason that they had 30 years of development, and we just started. Still now there are 6 laboratories all over the world. Also in Italy, by the way, there is a very nice group in Lecce with Daniele Sanvito working on this topic, who study static polariton qubits and different their realizations actually. So double and quadruple optical traps for polariton condensates are under study and being optimized. And as you saw here, Ising simulators based on polariton qubits are being developed. The Chinese consortium that I represent as a Chinese professor now, it goes in four different directions, developing different material systems for quantum polaritonics. And there are actually best Chinese universities involved in this research. So we cautiously hope that some significant progress will be achieved very soon. For more information, we recently published this review paper in Nature Physics, and where we talk about polariton condensates for classical and quantum computing. And I would be also very glad to answer your questions. So thank you very much for your attention.